All right. So when we talk about correlations, correlations have their own benefits. With observational strategies, as I talked about in the previous video, observational strategies allow you to describe behavior. When it comes to correlation, correlation now allows you to predict behavior. Now, can you also describe behavior with a correlation? Yes. But the new thing you can do, the added value of a correlation, is allowing you to predict a behavior. Now, when we look at a correlation, we look at a correlation coefficient. And a correlation coefficient is the numerical value of the strength of the relationship. And you're going to see two parts to a correlation. You're going to see the sign and the number. The sign only tells you the direction of the relationship. So you're going to either see a positive sign or a negative sign. And I'm going to explain that shortly. The magnitude is the number. And the number for a correlation can go from 0 to 1. 0 being there's no relationship whatsoever, and 1 being a perfect correlation. Now, here's the deal. It is exceedingly rare that you get a perfect correlation of 1.0. And the only way you could predict with 100% accuracy is if you had a perfect correlation. So what I want you to understand is that while correlations allow you to predict, it's not with 100% accuracy typically. Usually it's imperfect prediction. So let's talk about it. I said that the sign is going to be either positive or negative. A positive correlation. The word positive suggests that both factors are trending in the same direction. That means to say if factor A is increasing, factor B is increasing. If factor A decreases, then factor B also decreases. So positive correlation, we refer to as a direct relationship. Both factors go in the same direction. So an example of a positive correlation would be smoking and cancer. The more you smoke, the greater the risk of developing lung cancer. Right? We know roughly 90% of 90% of the cases of lung cancer involve smokers. So, can we predict based on your frequency of smoking your likelihood of getting cancer? Yes, to some degree. Now, if a person doesn't smoke cancer or if a person doesn't smoke cigarettes, their rate of lung cancer decreases, right? So you see it's going to increase or decrease depending on smoking. Your cancer rates are going to both increase or decrease. Now, a negative correlation, the factors are going in opposite direction. So as factor A increases, factor B decreases. So what would be an example of something increasing and the other thing decreasing? Well, the more you exercise, typically, your weight tends to go down, right? Because when you exercise, you're burning calories. And the more calories you burn, the less weight you typically have. And if you burn, let's say, 3,500 calories, that's roughly a pound. Now, typically, people don't have a calorie deficit of 3,500 calories in a single day. But across a week, it's not uncommon for a person who's trying to lose weight. They might run on the treadmill every day and they burn 600, 700, 800 calories, let's say, if they're running at a slow pace, and that adds up. So the more you exercise, then you're going to decrease your weight. That's kind of an example. Another example might be the higher gas prices are, the fewer miles you're going to want to drive in your car. Does that make sense? As one's increasing, the other's decreasing. Now, when we talk about a negative correlation, that goes from 0 to negative 1.0. Now, in the context of positive and negative, negative does not mean bad. It just means it's an inverse or indirect relationship. So the sign, as I said on the previous slide, only tells you the direction of the relationship. So we talked about positive and we talked about negative correlations. Now there is another possibility. No relationship. There is a possibility that factor A is entirely unrelated to factor B. Something like exercise and intelligence, right? Exercise is unrelated to intelligence. So if you ran a correlation, you would probably get no relationship whatsoever. Now, this is how we conceptualize linear relationships. There is something called a curvilinear function, but your standard correlation or your Pearson correlation cannot detect a curvilinear function. That's why we're not talking about a curvilinear relationship on this slide. So let's look at what the scatter plot would look like. And a scatter plot is just the series of dots and what they might look like. The top panel shows you where you have a perfect relationship, whether it be perfectly positive, which is sloped upward to the right, or perfectly negative, sloped downward to the right. You know you have a perfect correlation when you could connect all the dots with a single straight line. But in reality, most of the time you don't have a perfect correlation. You have a spread of dots. Now, on your top panel in the middle, that would be no relationship where all the dots are scattered. Can you detect a trend line in these dots? The answer is no. It's not upward to the right, it's not downward to the right, it's just spread all over. Now, correlations, as I said, are very rarely perfect. Now, even if you think you had no relationship, it is possible to have a very weak correlation where you have a very small sign. Anywhere from 0.3 and below is a weak correlation. So if you look at the bottom panel, this is kind of what you would see in real life. You'll notice that you're not able to connect all the dots with a single straight line. So the dots are spread all over the place. But if you see the greenish highlight, that's showing you the trend of the dots. So it's on the bottom left, it's sloped upward to the right. So we would say that there's a positive correlation between maternal warmth and a child's compliance. So the warmth and love provided by a parent increases the likelihood of a child listening, right? On the bottom right, we see a green highlight slope downward to the right. So that's a negative correlation. And this would be as maternal ignoring increases, child compliance decreases. So they're going in opposite directions. But what I love about comparing the top panel to the bottom panel is you can see that in reality, you don't usually get the dots lined up in a single straight line. You don't get perfect correlations. Now, if you look at the bottom correlations, which correlation is stronger? The bottom panel on the left or the bottom panel on the right? What would you say? Anyone have a belief? Jessica, is the bottom panel on the left or the bottom panel on the right a stronger correlation?
Wait, I think there's two. This me or?
I'm sorry, Gavoronsky. Sorry. Jessica Gavoronsky.
I would probably say the one on the left, since it's a positive correlation.
Okay. By show of hands, how many of you agree with Jessica? So we have 6 people in the class who agree with you, 8 people, 9 people. Is there anyone who, 10 people? All right, we could drop the hands. Is there, so half the class agrees with you. Is there anyone who believes that the panel on the right is actually the stronger correlation? I see Evan, Fan. So we have 3 hands so far. Teresa. Now, that means that there are 7 of you who did not vote. But what if I told you, even though Evan and Fan are in the minority, they are correct? Please remember what I said a couple slides ago. The sign only tells you the direction of the relationship. Positive does not mean greater. Positive just means both factors go in the same direction. So if you were to ignore the sign, which is what you're supposed to do when determining the strength of the relationship or the magnitude of the relationship, which decimal point is higher, 0.34 or 0.41? 0.41, right? So if you look at it, 0.41 is closer to 1.0 than 0.34 is, right? So the bottom right correlation is stronger than the bottom left correlation. So again, I don't want you to lose that point. It's very, very important to understand the sign tells you only the direction of the relationship. The decimal point number tells you the strength. So once again, and the last time I'll say it for this one, the bottom right has a stronger correlation than the bottom left. So on the previous slide, you saw that there were a series of dots. The series of dots you saw on the previous slide are what we call a scatter plot. So all of those dots reflect the trend of the relationship, if that makes sense. So how do we shade it? Now you saw the green shading sloped upward to the right or downward to the right. We would create what's called a line of best fit. A line of best fit tells you the general trajectory. Now, with the line of best fit, if it were a perfect correlation, you should be able to connect all the dots with a single straight line. But notice how there was this wide shading going down or up, because in reality, it's rare to get a perfect correlation. So we would show like the trend of the relationship. We still would have a line down the middle, but what would happen is the spread of dots from that line would suggest variability or error. And with that, we would also see the wider the spread of the dots, the weaker the correlation, because there's more error there. Now, by the way, that slide should say amount of error. It's missing the A. Forgive that. Now, we said in the previous video that descriptive observational methods allow you to describe behavior. Correlational methods allow you to predict behavior. But being able to predict an outcome is not the same thing as saying factor A causes factor B. So correlation and causation are not the same thing. So if you have a correlation, factor A could theoretically be causing factor B's response, but also factor B could be causing factor A's response. And there are an infinite number of outside factors that could be influencing both A and B. These are the 3 reasons why we cannot say a correlation is causation. We don't have the ability to have cause effect because we have bidirectional relationship. Maybe A caused B, but maybe B caused A. And if we can't say definitively that the first factor led to the second factor's outcome, we don't have a cause. And the fact that there are an infinite number of outside factors, which we call the third variable problem, we can't account for all of that. So where does that leave us? Correlation allows us to predict pretty nicely, but we leave causal relationships to experiments. With an experiment, you can determine cause and effect. Now, I'll give you the example. Is it possible that low self-esteem could lead to depression? The answer is yes, of course. Is it possible that depression could lead to lower self-esteem? The answer is yes. Now, which came first, the low self-esteem or the depression? That is the chicken egg problem, right? We don't know which one came first. And if you studied 100 people with depression who also have low self-esteem, some, the low self-esteem would have preceded the depression, and others, the depression would have preceded the low self-esteem. So we don't have a clear direction. Moreover, there are outside factors that could cause both low self-esteem and depression. Let's say a person experienced a trauma, a physical trauma, which created, I'll use it, a veteran went to war and had some explosive device occur and they lost their legs. Could that trauma result in both low self-esteem and depression? The answer is yes. So even if low self-esteem is linked to depression one way or another, there are other things that could cause both. So we have to be mindful with correlation. Correlation does not prove causality or causation. So we also have to avoid the potential for illusory correlations. Sometimes we look for patterns in random events. Sometimes we expect there to be a relationship when in reality it was purely random. So if we look at coin flips, and I want you to look at the three options. The first option, 3 heads and then 3 tails. The second option, head, tail, tail, head, tail, head. And then the last option, 6 tails in a row. If I were to ask you which of these is more likely, what would you say? Which of these 3? The first, the second, or the third? So I have a couple answers saying the second. And that is what I would expect your answer to be. But what if I told you that in reality, all 3 of these outcomes are equally likely? Now, most people do pick the second one. So I don't blame those who thought the second one. It seems like, what are the odds of getting 3 heads and then 3 tails? What are the odds of getting 6 tails in a row? You might think, hey, the one that's more like seemingly random is the most likely. But mathematically, the probability is equal. Every time you flip a coin, there is a 50% chance of it landing on heads and a 50% chance of it landing on tails. Equal likelihood. And as long as you flip the coin the same amount of times, no matter if you had 6 tails in a row or 3 heads and 3 tails, that's actually equally likely to having a head, tail, tail, head, tail, head. So they're all equal. And if you went from this very restricted sample size and flipped a coin 1,000 times, you would find sequences of all 3 of these, because mathematically they all appear, and mathematically they have equal likelihood of appearing. So that is our knee-jerk reaction. People who are gamblers. So people say, oh, I want to play at this table because it's a hot table or a cold table. Well, I got news for you. There's no such thing as a hot or cold table. The table is just a table. The cards are the cards. And if you play the string of cards out enough, you're going to lose your money. There might be a short period of time where you go on, quote unquote, a run. But if mathematically, the run for the positive is the same likelihood as the run for the negative. So, but there's always a casino advantage. So if you play long enough, you're going to run out of money. Interesting, right? So flipping a coin, playing at a card game at the casino, and even in sports, you know, there is the mindset of feed the hot hand. So you pass the ball to the person who's making the shots. But if you follow that person across a season, more often than not, their average is roughly the same. So the hotness is balanced out by the coldness, so to speak. Now, even a singular shot, that being said, of the hotness and coldness of a shooter, every shot is viewed as an independent behavior. So let's take someone like Shaquille O'Neal. Now, Shaquille O'Neal was one of the greatest basketball players of all time, but he was incredibly poor at shooting foul shots or shooting from the free throw line. And he averaged something like a 40 or 50% success rate where he would make the shot. But let's imagine you are betting on Shaquille O'Neal. And Shaquille takes his first free throw shot and he makes it. He takes his second free throw shot and he makes it. He gets fouled again, takes his third free throw shot. He makes it again. Gets fouled a fourth time. Pardon me, he takes a fourth free throw shot and makes it, gets fouled a third time, and then he makes it again and again. So now Shaquille O'Neal, that you know has roughly a 40 to 50% free throw percentage, has made 6 in a row. If I were to ask you, is he going to make or miss the 7th free throw shot? The answer is we don't know. But the probability is equal because there are only 2 outcomes. Either he's going to make it or miss it. So it is independent of the previous 6, though, because you could argue both sides of the argument. On one side, you could argue, hey, he's made 6 in a row. He's hot. So he's going to make the 7th shot because he made 6 in a row. Or you could argue, hey, he's made 6 in a row. His percentage is about a 50% free throw percentage. He's going to regress towards the mean. He's going to miss it. But in reality, that 7th shot, the likelihood of making or miss is independent of the previous 6. Now, if you follow Shaquille O'Neal, now he's retired, but if you follow him across the season, the percentage would even itself out. But does that make sense? That 7th shot is independent of the previous 6? But our mind naturally looks for patterns. And sometimes we create patterns in random events. That, my friends, is called an illusory correlation. So is that clear? So that's correlation. Now, the next piece is going to be on experiments.